Okay, so good afternoon, everyone. I will talk about spin dynamics from second principle in MULTIBINIT. Oh, okay. So my talk, I will have my talk in 3 parts. Sorry, what happened? It's okay. Okay, thank you. So first I will talk about the abstract data structure in MULTIBINIT, which will help us to to implement potentials very easily. And second part I will talk about spin dynamics in MULTIBINIT, and then the third part I will talk about the ongoing development on the spin lattice coupling in MULTIBINIT. As you can see from the previous talks also, we have many degrees of freedoms in MULTIBINIT, and we maybe even we may even come to more of them, and which we even don't know what it is yet. So how to make them work together? So what we do is we design abstract data structure in MULTIBINIT. First, what we want to do is to separate the physics from the implementation details. So we designed a 3-layer structure. On the bottom layer, we have the low-level things like the mathematics, symmetry, MPI, I/O, and supercell builders and cell structures. And on the middle level, where this is the physics. Okay, yeah. Okay, so on this level is where the physics are, and on the top we have a manager which will tell the users what are the logics, what will be done, and the second design principle is that each part should be able to work as a black box. So, for example, if we add a scale up as a new potential, we don't have to know every detail about all the other potentials, and when we add it, it should just work. And for example, if we want to add a new mover, like we want to use an external MD library, we can just put it there, and it should work. And what we want to do is keep the consistency between the potentials. If, for example, if we go to a very large supercell, the inactions and the spins should still know what are their corresponding lattice atom. So I will talk about in detail the physics layer here about the potentials and the movers. So for the potential, we first have a potential in the unit cell. So we can use internal fitting to get the potential in the unit cell, or we can read from external output, like from NIDDB and 190. And in each of the unit cell in the potential, we make abstract. We make abstract potential for the primitive cell, and each of them have a few neighbors, and they should have a few functionalities. Using this primitive potential, we can build supercell potentials using a helper class, a supercell maker. So each of them should be easy to go from primitive cell and supercell, and they should be consistent. And the most important one, the physics, is in the potential. So each of the so we have abstract potential class which define a few things like what is the potential, and each of them should be able to calculate the energy, the derivative to the degrees of freedoms. And because many of the potentials are polynomials, we also build abstract polynomial potentials, so we can easily build these kind of potentials. We also have a potential NIST, which is also a potential. So what it does is to sum all of the output from the components, the energy and the derivatives up, and output it to the movers. We have a stream of movers. So for each degree of freedom, it has its own motion equation. And using this motion equation, we use the input from the potentials and update the state of the system. So each of the movers should have something like a run one step and do the update. Using this abstract data structure, we hope we can make the implementation of the potentials very easily. So the next I will talk about spin dynamics. So like what we have in the talked about in the abstract potential, we should have a Hamiltonian, which for the spin we have the exchange, interaction energy, the single ion entropy, Janoshinsky-Molia, and dipole-dipole interaction, and we also have the energy due to the external field. And from this energy, we can calculate the derivative, and then we get effective magnetic field. Using this magnetic field and add the thermal path, we can use the stochastic non-Lifshitz Gilbert equation to update the spin orientations. So to build this model, we use a method which was proposed by Liechtenstein in more than 30 years ago. And we use local spin rotation as a perturbation. And well, because MULTIBINIT is plain wave code, the local spin rotation is not already there. So we have to use one function as the basis set. So we use 190 to build a tight binding like Hamiltonian, and then use the Green's function, and then we can calculate the response by rotating two spins and get the exchange parameters. So this method is implemented in a Python package, which you can download from the MULTIBINIT GitLab. We have the exchange parameters implemented, and the single ion entropy and Janoshinsky-Molia will be soon implemented. Let's see a few examples. So this is from the parameter building package. We can calculate the effective Magnum dispersion curve, and we have some snapshot of the spin configuration. As you can see, some scamions and strapped domains. And we can also calculate some thermodynamics properties, and this is for lanthanum ferrite. Next, I will talk about spin lattice coupling. First, we build a lattice Hamiltonian for reference spin configuration. Then we can write the total energy of a system as this plus energy difference from that. So then we can expand this delta E as a tiny expansion of the lattice as atomic displacements. We do it to the second order. And if we consider the spin system as a Heisenberg model, then we can write we can define two parameters, which is the first derivative and the second derivative of the exchange parameter to the atomic displacement. And from this model, we can calculate the force and the change of the exchange parameter and the effective magnetic field from these parameters, and then we can plug them to the motion equations and calculate the updated displacements and spin. As you can see, these two quantities can already be computed from DFT, so we can use that to feed the parameters like the OIGU and TIGUV. So we have two methods to do that. One is to feed them to the forces from DFT. The other is to feed them to the exchange parameters. We also have another method which is pure perturbation theory. So I won't go to the details, but I want to show that every term is already there, like the Green's function from tight binding. And here we need, what we need is inection phonon coupling using the one function basis. For OIGU, we need only the first, so I think we can get them easily from MULTIBINIT. So what we need to do for the second order one is we need some second order inection phonon coupling parameters. I hear that there's a lot of development now in MULTIBINIT, and I hope I can get some enactment from that. So now we can calculate the forces and the spin effective magnetic field from these coupling terms and from the lattice and pure lattice and pure spin terms. Then we can do all the dynamics, do the two dynamics at the same time. After that, we can do some processing to get the observables which are affected by the spin lattice coupling. For example, the change of the average position, the magnetic moment, or we can also calculate like the shift or the bandwidth of the phonon or Maclaurin dispersion curve and things like that. So to summarize, what we have done is we implemented the generic data structure for MULTIBINIT. It is implemented and it is already used in spin dynamics. It is pure Fortune 2003. We have implemented the spin dynamics, and we can have the exchange, DMI, single ionicity, and external field. We have the LLG equation for spin dynamics, and we can also do Monte Carlo. We can get the exchange parameters from the TB2J package, which you can download from GitLab. We can get many observables from the dynamics. The documentation is already in MULTIBINIT. It will be in the next version. And we are now implementing the spin lattice coupling. The algorithm being tested in the Python package. And we have several methods for the parameter fitting. It is yet to be tested which one works the best. And we have started the implementation in MULTIBINIT. Hopefully, we can see it soon. Thank you.